based on Faraday's law. And what does this equation tell you? This equation tells you, again, this is the cause, this is the effect. It tells you time-varying magnetic fields produce electric fields. So if at a given location, the magnetic fields are changing with time, you will have an electric field produced there. Okay, so for instance, we've talked about this law last chapter. So let's say there's a magnetic field here, and let's say you somehow increase this magnetic field or you change it with time, and this will create an electric field all around here. And the configuration of the electric field will be like so. So the electric field will be like that. Okay. And if you stick a wire, you'll get an EMF in the wire, and that'll drive the current. Okay. And again, like we've said, this electric field is non-conservative. Okay. So it's different than what's produced by charges. All right. So this is the electric field, but it's hard to maintain this increase of magnetic field. How do you do that? Well, one way to do it would be, you can grab hold of a magnet and move it like that. And then you could increase the magnetic field in this region. You could create that, but and then you run out of space and stuff like that. You could jiggle it back and forth. But the easiest way to do this is the following. Okay, so if you pass a current in a loop of wire, you're producing a magnetic field like that. And if you want to keep changing this magnetic field, what do you think you could do? Yeah, so you make this current AC current. If the current is flowing like this, back and forth, then you're continuously changing the magnetic field. You're inducing an electric field here. Okay, and you can stick a wire there and you can have a current. Okay. So this is the principle behind a lot of wireless charging. This is the principle behind wireless charging. Okay, so you're transferring energy from here to there. Okay. All right, so that's what this chapter is about, induction. Okay. So let me start off with an application. You guys might have heard of induction stoves. Okay. So here's a coil, just like I said here. You apply an AC current to this. So this is producing a changing magnetic field, which will induce an electric field here. And if you have a metal cooking utensils, that electric field will drive a current there. And that current, because of the resistance, turns into heat. So you're transferring energy from here directly to the pot. This doesn't get hot. You're not wasting any energy there. All the energy is being transferred. Okay. So the only thing is you can't cook on a ceramic pot here. You have to have a metal pot. This stove is the most efficient. So an induction stove is about 90% efficient. A gas stove is only 50% efficient. You burn the gas, the flame, and you're losing a lot of heat. Electric coils, so you're heating a coil and putting the pan right on top of that, and heat goes via conduction. That's only about 70%, 75% efficient. And radiant stove, you're again heating a coil, and that coil is radiating, and heat is conducted through this plate to there. And so that's also inefficient. Okay, the induction stove is the most efficient. Okay. And that's how your wireless charging works on the phone. You guys might have these chargers. Here's a transmitting coil. You send an AC signal to that. Here's the receiving coil in the phone. That's you're inducing a current there via the changing magnetic field. Now, the problem is, so this is an AC current that you're getting. That AC has to be changed to DC before you charge the battery. Same thing with the Tesla. You have a coil for wireless charging of the Tesla. You have a coil here. You're supplying an AC current. There'll be a receiving coil. You're getting an AC electric current, and then a rectifier. You have to convert that AC to DC before you charge the battery. Okay? And we will talk about how to convert AC to DC in the next chapter. Okay? So wireless charging efficiency can be up to 90%. What's the difference between this and maximum charging? Maximum efficiency. When do you get maximum efficiency? When do you think you'll get maximum efficiency? When the receiving coil is right on top of there. If the receiving coil is over there, you lose out on the energy transfer. Okay? So to make sure that the receiving coil is right on top of that, nowadays those phones have the magnets that just align the receiving coil and the transmitting coil. You guys know what I'm talking about? Okay. All right. So again, this entire chapter is based on this equation, Faraday's law. Time-varying magnetic fields are producing electric fields. Okay? And so, for instance, if this field was increasing, like this magnetic field was increasing, it would induce an electric field like that. And of course, it's inducing an electric field everywhere. The further out you are from the changing magnetic field, the weaker that field is. Okay? All right. So again, how do you change this magnetic field? The most easiest way is if you have an AC current in this coil, this magnetic field changes and it induces electric fields. Now, sometimes this can be a nuisance, okay? So mutual inductance can be a nuisance in electric circuits. If you have an AC circuit, varying currents in one circuit produce magnetic fields which can induce a current in another circuit. Induce unwanted EMFs in nearby circuits. Okay, so I think back in the old days, if you had several machines on the floor, on factory floors, when you shut down one machine, at the end of the day, you're shutting down one machine, so that's changing current, it's inducing changing magnetic fields. It would turn on the neighboring machine. You guys understand? It will induce a current. Okay. So you can never shut down the factory, and then you would have to invent some kind of magnetic shielding. Okay. Anyway, I think that's not a problem anymore. So the most important useful application of mutual inductance today is transformers. What do transformers do? Mm-hmm.
Transform electrical energy to other types of energy.
See, here's where the name should. So transformers, they step up and step down voltages. Okay, so here's an AC source. Here's a coil. You apply a AC voltage to the coil. It's producing a magnetic field which is changing. If you use a magnetic material, this magnetic field can be coupled to this secondary coil. What this is doing is the job of, you want maximum coupling between two coils, and that's when they're right on top of each other. But if you can't do that, then you use a soft iron and magnetic material, and this magnetic field is coupled there. So this changing magnetic field induces a voltage here. And what this equation is telling you is the voltage here, the amplitude of the voltage in 2 is N2 over N1. N2 is the number of turns over N1 times V1. So if this N2 was 100 times bigger than that, N2 was 100 times bigger than that, the output voltage is 100 times bigger than the input voltage. Free lunch. What gives? So power input will always be equal to power out. Power input is V in, I in, equal to V out, I out. Okay, so if you have output voltage that's 100 times greater than the output current is 100 times weaker. Okay, so no free lunches. Yeah. Why do we want to step up voltage?
Different machines need different types of voltage to work. So I can have one power source and I can use it for multiple things.
Yep. And in power transmission, if you transmit at high voltage, then the power losses are minimized. Okay, so that's one better. All right. So transformers is, again, you're using changing magnetic fields, time varying magnetic fields to induce an electric field. Okay. So this is what you want to remember. Changing magnetic field is inducing this, so an increasing magnetic field will induce an electric field like that. So the best way to change a magnetic field is to have an AC current in your primary coil, which will induce a AC voltage in the secondary coil. All right. So the most important application is that, and you just saw how induction stoves work in principle, and they're the most efficient stoves. Yeah. So mutual inductance is, that is telling you how much, what kind of EMF you're inducing in the secondary coil when the rate of change of current in the primary coil is that. Okay. And if the coupling is stronger, the mutual inductance measures the coupling of this. So the mutual inductance is the proportionality constant. The EMF induced in the secondary coil is proportional to the time rate of change of current in the primary coil. Okay. Now, based on everything we've said, if I move this coil further away, let's say the coil was placed over here. Okay, if coil 2 was placed over here, what would happen to this number? Go down, very good. Same distance if it's here. Done. Okay, so that's what that mutual inductance measures. Okay, so see, it depends on the configuration, so we can't give you a clean formula for it. Okay, so it's something that you would have to measure, but in certain configurations, we'll give you a formula for that. Okay. So now you saw how an induction stove works. You apply an AC voltage to this primary coil, which changes the magnetic field here, which induces an electric field here, and if you have a metal cooking device, then you'll induce a current, and the current flowing in that device will eventually dissipate into heat. Yeah. And because they're very efficient, you're cooking everything faster, and you're, again, 90% of the energy is transferred. You're cooking stuff faster, and that's saving you energy as well. So wireless charging also works that way. Here's the primary coil. Here's the receiving coil. Okay, and they put magnets on the cases, so the receiving coil is aligned with the primary coil. Okay. So here is the magnet on the case. Okay. And again, all this is possible because the receiving signal is a AC signal, and you have to convert that to DC before you can charge the battery. But all that is possible because now you can have miniaturized circuits and stuff like that. Okay. So there's a lot of stuff that's packed in here. But the most important thing that's packed in here, okay, we'll talk about it at the end of this chapter. The heart of that thing, device. All right, so here's wireless charging. Here is a solenoid. This has special properties. Okay, so let's say you take a straight wire. So you can take this wire and unwind it and make it a straight wire. Its resistance doesn't change. Its resistance would be the same. Okay? And if I connect that wire to a battery and make this, if I crank up the voltage, the current would increase instantaneously. Okay, if the wire was straight. Now all I'm going to do is take the wire and wind it up into a solenoid like this. Okay. Now if I wind it up into a solenoid, here's what's happening. As the current is increasing, this coil is producing a magnetic field. That magnetic field is increasing. That magnetic field is threading the next coil, which is inducing an EMF in the next coil. The EMF is in the opposite direction. It's trying to fight an increase in the current. Now, you took the same wire, wound it up into a solenoid. Now, if you crank it up, this coil is going to fight them. The same wire, its resistance didn't change. Now it's acquired a property that it doesn't like changes in currents. Okay. So if you try to increase, if you try to increase a current, the voltage is in the opposite direction, trying to fight the increase in current. If you try and decrease the current, the voltage is such that it's trying to maintain that current. This fellow just doesn't like changes in currents. You'd connect an AC voltage to it, he's not going to like it. The higher the frequency, the worse he resists it. Okay, so this guy is called an inductor. Okay, and what he can do is, well, he doesn't like AC currents. We'll talk about this next chapter. And he also stores energy in magnetic fields. So anytime there's a current flowing through this guy, there's a magnetic field in here. Remember, we talked about it in the Large Hadron Collider. You had that huge cylinder packed with sensors, and there was a solenoid around it, producing a magnetic field in that cylinder. Okay. All right, so we'll talk about this. So self-inductance, a coil like this, when you pass a changing current through it, it'll produce an EMF. And what is the EMF doing?
Fighting the changing current.
Very good. Okay, it's fighting the changing current. If you're trying to increase the current, it's going to produce an EMF in the opposite direction. Okay. What happens to the EMF when the current stops changing? It doesn't do anything. Okay. When the current stops changing, the magnetic field is not changing, and that's not inducing an EMF. Okay. All right. So if you, through an inductor, if you try and increase the current, it'll produce an EMF in the opposite direction, and that EMF lasts only as long as the current is changing. And if you're decreasing the current, the EMF is such that it wants to keep the current steady. Okay, so for a coil like this guy, the self-induced EMF is proportional to the rate of change of current, and the proportionality constant is called the self-inductance. Okay, so L is the inductance of the coil. And for this guy, we can give you a formula. Okay, so for a closely wound solenoid of N turns, And by the way, N is, so the self-induced EMF is, N is the number of turns, and this is the rate of change of flux through each turn. Okay, so the EMF is that. We won't use that formula much, we'll use this mostly. Okay. So in the exam formula, I have put this formula, but we won't be using this much. Okay. So the self-inductance is given by mu naught N, little n is the number of turns per unit length. N is the total number of turns, and L is the length of the solenoid. A is the area of cross-section of the solenoid. A is the area of cross-section. L is, again, the length of the solenoid. Okay, the self-inductance. So this is voltage, current, time. So voltage seconds over ampere. Those are the units of that, and that combination is called a Henry, after Mr. Henry. Okay, so what does L tell you? It tells you how hard it fights changes of currents. Okay, so larger L is greater the induced EMF for a given rate of change of current. Okay. So oftentimes you want larger L's. So this is mu naught is the permittivity of free space. So if you want to increase L, what you can do is if you pack this thing with magnetic materials, you can increase L. Okay. So if you pack it with magnetic material, that mu naught gets replaced by mu m, and that can be like 100 times greater than this guy, than mu naught. Okay. So if you pack this thing with magnetic material, you can increase its inductance by a factor of 100. Yeah. We nearly took your dollar, Sophia. Yeah. All right, so you have learned about an inductor. This is a new electronic piece of equipment. So now what you want to do, you want to put it in a circuit and see what its behavior is. Okay. So here's the first thing we'll do. Okay, we'll consider the simplest circuit. We'll take a resistor and an inductor. Okay. And later down the road, what other electrical equipment have you heard? Electronic piece of equipment you've heard of?
Toroid?
Huh?
Toroid?
Capacitor. You learned about capacitors. So we'll put a capacitor in there. Okay. So right now we'll just put a resistor and an inductor. Okay. So here's this guy. We'll close the switch, and now we've started our timer. So that's time t equal to 0. When you close the switch, if this guy was not present, so the behavior of the circuit would be like this. Okay. So when you close the switch, if this guy is not there, if only the resistance is there, what happens is the current is 0 before you turned on the switch, and as soon as you turned on the switch, the current goes to its value. I will be equal to E by R. It instantly rises to that value. Now with this guy present, so this guy is an ideal inductor. He only has inductance, no resistance to it. Okay. So we're going to do the same thing with him present. What do you think is going to happen? Okay, so the current is going to be 0 till you close the switch. And now you close the switch, what do you think will happen? What does this guy do?
It's going to increase more gradually.
Yeah, so he doesn't like changes in current. He fights back. He produces an EMF in the opposite direction. And so the current will rise more slowly. It rises exponentially. And it will eventually get to that value, the steady state value of E over R. So that's what happens. Okay? Now here's the deal. This kind of stuff, this change happens over millisecond time scales, depending on the value of R and L. Okay? But we are interested in that kind of stuff. Okay? So that's what we want to study. How does the current rise? Okay, so we want to get an expression for I t after you close the switch. So how do you go about it? All right. So we've come up with a standard standard procedure. Here's your system. What do? You come up with a mathematical model. And that's how you study. That's your standard procedure of studying. How do you come up with a mathematical model? Some kind of principle, engineering or physics principle. It's mostly physics principle. What kind of mathematical model is this? What is a mathematical model? Generally is a differential equation. Then come up with a solution. Yeah. And if the solution is not agreeing with the experiment, then you refine the model. Okay, so that's your standard procedure. You keep refining the model till you get correct model. Okay, so here we are going to close this thing. Right, I'm going to erase a bunch of stuff. Well, we'll do it later. Okay, so we're going to close this switch. And now we want to study the time evolution of this system. Okay? So the principle that will go is, we know Kirchhoff's rule. Kirchhoff's rule one of Kirchhoff's rules says the sum of the voltages across all the elements add up to 0 around a closed loop. And that's the principle that's going to give us this mathematical model. So the principle that is going in is Kirchhoff's rule that is giving us the mathematical model. Okay. So we'll start here. When you go across here, the change in voltage is plus E. And then you're going from high voltage to low voltage, it's minus IR. And then this guy doesn't like changes in current, so he's producing an EMF in the opposite direction. And so you're going from high to low, it's minus L di by dt. Yeah? So as long as this guy is non-zero, this guy is producing a EMF in the opposite direction. So there's the differential equation. There's your mathematical model. And so now you want to solve this. So again, let me write that I is a function of t explicitly. All right, so solve this differential equation, and here's the solution to that differential equation. See, at t equal to infinity, this term is 0, and the current goes to the steady state value E by R. Okay, so there's the steady state value. For t equal to 0, that is 1. 1 minus 1 is 0. At t equal to 0, the current is 0. Okay, so it's rising like that. This guy is the time constant. The time constant tells you over what kind of time things change. Okay? And the time constant is given by L over R. Okay, so the larger L is, the greater the time constant. The larger L is, the stronger he fights against changes in current, and the longer it takes for the current to go to the steady state value. Okay? And the smaller R is, larger the time constant. So L, the time constant is L over R. Okay, so the current rises exponentially to its steady state value of E over R. And like I said, again, in most situations, this time constant is of the order of milliseconds. Okay, so in most of our applications. All right, so now we are building up towards the most important one of the more important circuits that we use in our lives. Okay, so here's a circuit where you have an EMF, and what we'll do is when the switch is over there, the current goes through like that. It takes a few milliseconds, or let's say 100 milliseconds, to build up to its steady state value. Now you have a steady current flowing in here. And once you have a steady current flowing in here, what we'll do is we'll flip the switch from here to there. What happens when you flip the switch from here to there?
We'll just go through that secondary circuit. So instead of the full circle, it'll just be that right half.
Yeah, it'll just go through there. So by flipping it from here to there, what you've done is you remove the battery. Okay. Let's say I had I'm going to draw the same circuit. Except without the thing. Okay, so it's the same circuit without the inductor. When I flip the switch from here to there, by removing the battery, what would happen to the current?
Go to 0.
The current would go to 0 instantaneously. So at t equal to 0 is when I'm switching the switch. Okay. And what will happen is, with this circuit, the current would instantly go to 0. The presence of this guy, here's what it does. What do you think it does?
Tapers off.
Tapers. Right, so this guy, essentially that guy doesn't like sudden changes. Okay? So for this guy, when I flip the switch at t equal to 0, the current dies exponentially. Okay. All right. So what happens is the following: when you flip the switch, when the current is flowing steadily, you will learn this guy has storing energy in magnetic fields, and that stored energy will drive the current for a little bit till it runs out of energy. Okay? So for a few milliseconds, it'll drive this current. All right. So here's another diagram for that, similar diagram. So in this, with this thing, when the switch is closed, the current is flowing like that, and when this is closed, this will be open, and then you can, when this opens, this closes. Okay, so the dial does that. Okay. So when you remove the battery and this closes, okay, the stored energy in that will drive the current in the same direction, okay, till it runs out of energy. Okay. Okay, so the equation for this, when you close that, when you flip the switch from here to here, again, this is a closed loop, and the equation is as follows. So it's driving a current in the same direction, and when you go from here to there, you're going against the current, so it's plus IR, and then L. Okay, so it's driving, this is positive, this is negative, so the change in voltage should be negative. It should be, but it's L di by dt. I is decreasing, so this guy is negative, so it's L di by dt, and the change in voltage is negative. You come back to the starting point. So here's the differential equation giving you the behavior of this circuit. Okay, and you can solve this differential equation, and the solution is an exponential decay with the same time constant. Okay, tau is L over R. Yeah. So the steady state value of the current was E over R, and it decays. Okay. So again, once you remove the battery, the stored energy in this thing is driving that current for this amount of time. So now we'll give you an expression for the energies that's stored in this thing, in the inductor, okay? So energy is stored in magnetic fields. As soon as you drive a current through this coil, there's a magnetic field inside the coil, and we'll show you the current in the magnetic field. Okay. An inductor resists an EMF source from establishing a maximum current in the R. So, again, so here's this cup. I apply a force lifting it. What is preventing me from lifting it? Gravity. So I'm having to do work against gravity. And so since I did work, I've stored energy in it. I've stored potential in it. This guy is resisting the buildup of current. The battery is doing work to establish a current. So it's storing energy in this inductor. The battery does work to establish a steady current, and in the process stores energy in the inductor. Okay. All right, we'll close the switch. The equation, mathematical model describing the behavior of this guy is that, which we had already derived. Okay, so we'll bring this term to the other side. E times I is the power being delivered by the battery. And that is equal to, so E is IR plus L di by dt. And so if you multiply that by I, you get I square R plus Li times di by dt. But this guy can be written as d by dt of 1/2 Li squared. Okay. L is constant, I is the only one changing. Derivative of that would be 2I, 2 cancels, I times di by dt. Okay, so EI can be written like that. This is the power delivered by the battery. That's the energy it's delivering per second, per unit time. What is this guy? That's the energy dissipated in the resistor. And what is this guy? Okay, so if this is your rate of earning, this is your rate of spending, this is the rate at which your bank balance is increasing. This is the rate at which energy is being stored in here. Okay. So that is the energy. So du by dt is that. Okay, so the amount of energy stored in the inductor is 1/2 times L times I squared. I is the current flowing in it at any given instant. How is the energy stored? The energy is stored in the form of magnetic fields. Okay, so the energy stored is U is 1/2. Okay, we'll do it over here. U is 1/2 Li squared. 1/2 L is mu naught N square A L, and B is okay. And I square. B, the magnetic field is mu naught N I, so I is B over mu naught N, so I square is B over mu naught N square. Okay, and so if you simplify all of that, what you get is, when you cancel terms, what you get is this times AL. A is the area of cross section, and L is the length of the solenoid, so that's the volume of the solenoid. So the energy stored in the solenoid is this energy density, that's energy per unit volume, times the volume of the solenoid. So the energy stored in the magnetic field per unit volume is given by that. Yeah. You had an expression similarly for electric fields, which was E squared by 2 epsilon. So anytime you create electric and magnetic fields, you are storing energy in the electric and magnetic field. Okay. So that's the message there. All right, we already talked about this. So this is one of the more important applications of the Faraday's law, okay, changing magnetic field. So you apply an AC voltage, it's producing a magnetic field like that. And how are you coupling this magnetic field to this guy? To the secondary coil?
The magnetic, the soft iron.
This is using magnetic materials you're connecting, okay? So if this was not magnetic, then you wouldn't be able, that wouldn't couple, okay? So it has to be a soft magnet. That's, its magnetization is easily changed directions. You'll learn about hysteresis. If it's not easily changed, then a lot of that energy gets converted to heat. Okay, so it has to be easily magnetizable. Okay, and that's what a soft iron is. Okay. All right, so now this is one of the most important circuits in your life, or at least there are trillions of copies of this simple circuit. What is the circuit? It has a capacitor and an inductor. Okay, so before I get into that, let me show you a little app. So okay, so whenever a system like this oscillates, okay, this has three forms of energy. It has gravitational potential energy because this is going up and down. It has kinetic energy, and it has elastic potential energy because it's oscillating back and the spring is being compressed and stretched. Okay, so whenever you have a system that oscillates, you need to have multiple forms of energy. And all that is happening when a system is oscillating, energy is being converted from one form to another. Okay, how long will this oscillate? Forever, as long as there's no damping. Okay, so for a system to oscillate, you have to have multiple forms of energy, and you're converting energy from one form to another. Okay, all right, so here's a system. Okay, this fellow can store energy in the form of magnetic field. This guy can store energy in the form of electric fields. Okay, so the question is, will this guy oscillate? And indeed he oscillates. Okay, so let's do the following. To set it in motion, what did you have to, oops, oh, so here's no gravity. Oh, this, okay, so here, now in this case, there's only elastic and kinetic energy. Okay, so this is essentially a horizontal spring. Okay. So this guy is oscillating in what was it? Okay. All right. So what to get it? Yeah. Here's what I wanted to say. Yeah. So to get it to start oscillating, what you have to do is you have to initially give it energy, and then that energy is maintained. Okay. So let's do the parallel of that. We'll store energy in the capacitor. You charge the capacitor, you've stored energy in it, and now you let the system evolve. Okay. So once you charge the capacitor, what will happen is this charge will drive a current through there. current will start flowing like that. Okay, the capacitor is completely discharged, the maximum current is flowing, and then that current keeps flowing, and it charges the capacitor in the opposite direction. And then all the energy is drained from here, and the capacitor is fully charged back. And now the capacitor will drive the current again and oscillate and cycle through. All right, so once you charge this capacitor, what happens is current flows and keeps going back and forth. So this system will oscillate forever. What can stop its oscillation? What stopped the oscillations here? Damping, which is friction. Okay, so friction would stop the oscillation. Oops, this is. Okay, what do you think provides damping in a circuit? Resistance. Okay, damping. What does damping do?
Leads the energy off. So non-conservative.
Yeah, it converts good energy into heat. That's what friction does. Okay, so resistors convert that to heat. Okay, so as long as there's no resistors in this will keep oscillating forever. So what is the natural frequency of this guy? Okay, so here's the equation. Okay, so this is the energy stored in the, and again, what do you do to study any system? You come up with a mathematical model for it. Okay, so what is the mathematical model for this? Here's how you come up with this. Here's the principle. This is the energy stored in the capacitor. That's the charge at any given time. That's the energy stored in the inductor. And if there's no damping, if there's no resistance, time rate of change of that has to be 0. Okay, and so you get an equation like that. So I is d by dq by dt. Okay, so if you simplify all of this, this is the equation you get. Okay, and this equation is exactly similar to the equation for a mass attached to a spring. Xt d square x by dt square plus omega square xt equal to 0, where omega was k by m. Okay, k was the spring constant in that. So this equation is exactly like that. Here is your omega square. Okay. So that so you have oscillation, and the frequency of oscillation is 1 over square root of LC. So that's the frequency of oscillation of this guy. Okay. And so the question is, well, what use is this? That is the heart. That's at the heart of all wireless devices. That's how you speak wirelessly to something. So this is the basic tuning circuit. And how many copies of this circuit are there in the world? Trillions. Okay, so here's how you talk to this. Okay, you guys know of resonance. What is resonance?
When you apply energy to a system that doesn't, at the right time, so that it increases the amplitude of it.
That's right. So resonance is every system has a natural frequency, and if a driving frequency matches the natural frequency, then you can keep adding energy to the system, and you can set up large amplitude oscillations. If there's a frequency mismatch, then you can't continuously add energy to the system. Okay? So resonance is that. All right, so here's how it works. So now this was an ideal circuit. In real circuits, you do have a little resistance, which changes the natural frequency slightly. But anyway, nevertheless, this guy has a natural frequency. And if you have a room full of chatter, only the frequency that matches the natural frequency of this guy will set up a large amplitude current. These guys are not pumping energy at the right time, so they will they will induce energy, except that they will deposit very little energy. Okay, only this guy will deposit large amounts of energy. Okay, and then from this guy you can extract that information. So essentially, a transformer, you put a, so you're extracting energy from here by putting a secondary coil, and then this is the processing circuit. Okay. So this is the tuning circuit. You're catching the signal from that. You're transferring that signal to this circuit where, and then you're processing it. Okay. So, like I said, this is at the heart of any wireless communication. Yeah. So again, now let's analyze this circuit, a real circuit which has resistance to it, and again we'll come up with a mathematical model. Here is the mathematical model. Here's a way to come up with mathematical model. The energy stored in those two guys is that, and if a resistance is present, the resistance is bleeding energy at that rate. So the rate at which this energy is decreasing is equal to that. And here is the differential equation. Okay, and we'll compare it to this guy, a mass attached to a spring, and if this is in liquid, the resistance is given by that. Okay, so for the mass, for this guy, the equation was md square x by dt square plus b dx by dt plus kx equal to 0. Okay, so you see the parallel of that equation. Resistance, this is the friction coefficient. L plays the role of mass, and 1 over c plays the role of the spring constant. Okay, so this system and this system are governed by the same differential equation. Okay, that's why you learn differential equations. The same equation applies to so many different systems. Okay, you would never have thought that these two systems were cousins, right? And they are first cousins. Yeah. All right, so you can solve this differential equation, and there's Q. Yeah. You see the charge, the maximum charge in the capacitor is decreasing exponentially. And the altered frequency, the frequency of oscillation with damping present is that. Okay. And if the resistance is too large, if the resistance is large enough where this is equal to 0, it won't even oscillate. Okay. So the presence of resistance decreases the frequency. Okay. If resistance were 0, this term would not be present, and then the system would oscillate forever. Okay, the amplitude would not die down. Okay. So the circuit is critically damped if resistance is equal to that. Okay, the critical value of the resistance is that. All right, guys, so that finishes this chapter. Again, it was based on this equation. Time varying magnetic fields are producing electric fields. So a lot of applications, what we saw was you take a coil, apply an AC voltage to that produces a time varying magnetic field, which induces an AC voltage in a secondary coil. Okay. So that's what we saw. All right.